Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course on comprehensive view of speech processing. So today we are going to discuss about the linear prediction analysis of speech, and we are discussing this topic in the last lecture, and as well will also continue today also. So as we have seen in the last lecture, we briefly discussed about the importance of linear prediction analysis, in particular to the speech and its applications, and we also know that the speech linear prediction analysis is applicable to various other applications, and we discussed about how the linear prediction analysis or the LPC model is applied to speech, and different types of the way we can analyze the speech. One is the synthesis model based LPC model, where by using the LPC analysis we can able to generate the speech, and where in that case the system transfer function will be 1 over A of Z, that is like all pole system, and for that if you see the frequency response of the system will be like you can see at the pole locations we have the response will be very high, and these are known to be Foreman frequencies, and here the response is nothing but the vocal tract system, the response of a vocal tract system, or you can say the spectral envelope offered by the vocal tract system. And this is the synthesis model offered by respect to the LP analysis, linear prediction analysis, and this is your vocal tract system, and this vocal tract system is parameterized by using a set of coefficients known to be linear prediction coefficients, and this vocal tract system is excited by the excitation, normalized excitation, and again this excitation depends upon whether it's whether we are synthesizing the voiced speech or unvoiced speech. So based on that we have two types of excitations, and this normalized excitation is like multiplied by appropriate gain to get the output speech signal. And the same way we can also perform the analysis model, so in which here we will try to minimize the error. So in this analysis model, if you look at the system representation, where the speech will be given as input to a system, and here if you look at here the transfer function of a system is like the reciprocal to the synthesis model, where synthesis model the transfer function is 1 over A of Z, whereas in the analysis model, where if you look at here by looking at by deriving the error signal, and it's applying the Z transform over that, and by rearranging the expression you can able to see the E of Z by S of Z, where E of Z is nothing but the error signal, S of Z is nothing but a speech signal, and if you look at this expression in the system form, where E of Z is the output, that is nothing but error signal, and S of Z is the input. So and the system transfer function is given by A of Z, its inverse or almost like reciprocal to the synthesis model what we discussed over here. So therefore this is known to be inverse filter formulation. So using inverse filter formulation we can able to analyze the speech, and from that we can able to see what will be the error signal corresponds to the given speech frame. And if you look at the system, the response or the spectral characteristics of the system, the offered system in analysis phase will be, you can, since it is algebra system, you can able to see that the system response will be reciprocal to the one what we discussed in the previous synthesis model. You can see in the synthesis model the system response is like this, whereas in the analysis model the system response is just inverse to this, because it's A of Z there. So therefore here wherever the peaks were there you can able to observe the corresponding zeros, and then by analyzing the error we can able to derive the set of coefficients. Here in the ultimate goal of the linear prediction analysis is that by analyzing the speech frame we can able to derive the optimal prediction coefficients, so that the error can be minimized. So this we discussed in the last lecture, like here this is the error expression, like you can say that the mean squared error, and to determine the optimal prediction coefficients. So we need to we need to compute the derivative of the squared error, and then differentiate with respect to the a case, each of the a case, and then equate to 0. So we will get a set of equations, and by solving these equations we can able to get the optimal coefficients where the error will be minimum and all. So this is the standard formulation to compute the to determine the coefficients for minimization of error and all. So in this process we can able to see this is the intermediate result we obtain, and this by looking at this result you can able to apply the autocorrelation definition over here, and with this the expression leads to this form. And now this is like in this expression, if you look at this, consists of a set of for every I equals to varying from 1 to p, we have the corresponding relations. And now if you look at this expression in the matrix representation, you can able to see this R of I minus k by giving different values of k and different values of I. You can see that this is a p by p matrix, and then this a case is nothing but this is a coefficient matrix, and this is 1 cross p, and here you can see R of I is again like the p cross 1 matrix, and here by solving these the matrix expression you can able to get these unknowns a1, a2, a3, ap, right. So for solving this, if you solve this matrix relation expression in a normal way, you see the you can able to see the computation will be like a p cube by 3 and op square, that means order of p square operations are required for every set of for computing every set of for every compute every set of the p unknowns and all, right. And here this we have to perform for every frame, speech frame. And suppose for if you want to analyze the if you want to compute this LP coefficients for a speech signal of 1 second, and here we need to apply this LP analysis for every frame, and frames are overlapped the frames are shifted by 5 milliseconds. So therefore for a 1 second of a speech signal we have to around 200 frames. So for every frame we have to carry out this analysis for estimating the LPCs. So for every frame we have the complexity, or you can for computing these coefficients, the number of operations or number of computations that need to be performed will be p cube by 3 plus order of p square, and the storage that is required will be p square using a normal matrix by solving the matrix. But whereas since if you analyze this matrix, if you look at the matrix, here all diagonal elements are same, and the upper diagonal elements are almost like a replica of the lower diagonal, almost like you can able to see the mirror image kind of a thing, whatever it's very symmetry, you can see that with respect to the diagonal. So this is known to be Toplitzsch matrix, and now by applying appropriate reduction techniques like recursion techniques, we can able to optimize the computation. Here finally you can say by using Durbin's recursion, the number of computations that are required for computing the LP coefficients are the p square plus order of p. It's almost like linear order, right. And for storing the storage purpose also 2p locations are required for carrying out the analysis and all. And then the next part is that in the error analysis, if you look at here, this is the error, the squared error, this is the squared error, and here in the squared error, if you evaluate this expression here, error is nothing but S of n is nothing but the actual signal, and S hat of n is nothing but the predicted signal using the linear prediction coefficients. And now we need to our ultimate goal is that the predicted signal or predicted samples should be very close or almost like same as the actual one. That is the ultimate objective. So towards this, the error in the prediction can be computed by taking a difference, and then square of that gives you the squared error. And if you further simplify the squared error, if you can able to see that by substituting the results whatever we have achieved in the autocorrelation analysis or in the computation of LP analysis. So we got some intermediate result, right. So by this result we got it, and by solving this expression we can get the LP coefficients. And now by substituting this intermediate result in this expression of analyzing the error, analysis of error, you can able to see, finally you can able to see the error E equals to S of n square summation over n, where here n is nothing but the number of samples. Suppose for example, if your speech frame is 220 milliseconds and the sampling rate equals to 10 kilohertz, then this 20 milliseconds is nothing but 200 samples. So this n equals to from 1 to 200. So that way S of n square minus ak into S of n into S of n minus k. And now here this S of n square and S of n into S of n minus k, if you look at this, so these things are nothing but the autocorrelation coefficient. Like here S of n square is nothing but autocorrelation at the 0 shift, and S of n into S of n minus k is nothing but autocorrelation at the kth shift. So now this expression can be observed to be like S of n square is nothing but R of 0, and ak into where k varies from 1 to p, and S of n into S of n minus k, this is nothing but R of k. It is nothing but autocorrelation at the kth shift, right. So this is nothing but finally the error is nothing but R of 0 minus ak into R of k, where k equals to 1 to p. And now here this is the error, and now we can able to see that how this error is varying with respect to the number of, with respect to the coefficients, with respect to the prediction order, like where here the p is the prediction order. It means for computing, for predicting the present sample, we are considering the past p samples, So from the past p samples we are trying to estimate the present sample and all. So here for example, if you consider the p equals to 0, so it means that we are not at all considering, or we are not at all analyzing, or we are not at all bothered about the history at all. That means p equals to 0 means we do not know about the past history or the previous samples, and without any knowledge we will try to predicting the present sample. So obviously if we do not have any information about the previous samples and try to predict the present sample, it will be a random guess. It will be a random guess, and it tries to give it, obviously it provides the maximum error and all, the highest error. So therefore if you put k equals to 0, it means that this term will be like this ak into R of k, where k equals to 1 to p. Here k equals to 0 means then all these terms will be vanished and it remains only R of 0. What is R of 0? R of 0 is nothing but the signal energy S of n square. It is nothing but autocorrelation at a 0 shift. So it means that you will get a maximum error. That means if you do not have any knowledge about the past history, and if you want to predict the signal, so it leads to the error, maximum possible error. So R of 0 will be the error if we do not have, if you consider the p equals to 0, or if you do not take care about the history at all. So and then as the prediction order increases, then if you take k equals to 1 for example, then what happens, k equals to 1 means the a1 into R of 1. That means by knowing just the previous sample, we are trying to estimate the present sample. So for that, by knowing the correlation and all, then we can able to predict the present sample as some scaled version of the previous sample, That means k equals to 1 means now here the summation leads to only one term. It is nothing but a1 into like R of 1, a1 into R of 1. So it is nothing but and here you can see this one will be subtracted from this. So therefore now earlier the error is R of 0, now the error will be reduced by like R of 0 minus a1 into R of 1, So likewise if you increase the prediction order, that means instead of k equals to 1, suppose if you consider the past 2 samples or past 3 samples, past 4 samples, then we have some knowledge about the previous history or the nature of previous samples, and we know that since the samples are correlated, so by knowing the more and more previous samples, the prediction will be better, and that you can able to observe from this expression R of 0, and this one the second term, the other term, the summation term gives you the the previous samples, knowledge about the, based on the knowledge about the previous samples, right. When k equals to 1 means we considered only one previous sample, and k equals to p means by considering the past p previous samples, and each of these will provide some evidence, and then if you by considering the p samples, nothing but the summation will give you the p terms, and now r of 0 minus the summation of the contribution of the p terms. So, therefore, the error will be reduced. So, that way here the thing that need to be observed over here is that if you do not consider any the previous history or the previous samples, then the error will be maximum, and by considering more and more the previous samples, the error will be lowered, and this you can able to observe from this plot here. And here if you see, this is the error analysis plot with respect to the prediction order. So, when p equals to 0, you can see that it is the maximum, and here you can see the errors are plotted normalized plots with respect to r of 0, because when p equals to 0, the error will be r of 0. It is nothing but the summation of the squared samples, summation of the squared sample values. So, S of n square is nothing but energy of the signal. So, and now here, since we are here the scale is kept as 1, it means that here whatever the error analysis, whatever shown here in these plots will be normalized error, normalized with respect to r of 0, right, because you will get a maximum error as r of 0. So, that you can able to see here 1, it is nothing but by dividing r of 0 with r of 0 you will get 1, and afterwards as you increase the number of samples, right, for predicting the sample, present sample, the error will be come down, error will be reduced. So, that way here you can see there are two plots over here, one is the plot with a solid line, and another one is the plot with the dotted line, right, and here the plot with the solid line corresponds to the error analysis for a voiced speech, and the plot with the dashes, this indicates the error analysis for an unvoiced speech. We know that the voiced speech means this is the speech that is produced by due to the vocal folds vibration, and whereas unvoiced speech means the speech that is produced due to absence of vocal folds vibration, or but the excitation will be in the form of at different places of articulation by providing a constraint and the release of a constraint that offers the excitation, and that excitation is a noisy excitation. So, there because of that, if you observe the speech of unvoiced segments, the samples are not correlated, the speech signal appears to be noisy, and the samples are not the correlations among the samples are less that compared to the voiced speech. That you can able to see here, it is evident from here, you can see that as the prediction order increases, in case of voiced speech, there is a sudden decrease in the error for every for the increment of the prediction order. You can able to see that the error will be decreased, and error is decreasing drastically to a very lower value in case of voiced speech, because this is the reason for this is that because since the samples are correlated and they are very much related in the voiced speech. So, because of that, by knowing the more and more samples, or by increasing the order of prediction, increasing the number of samples for predicting the signal, the error in prediction will be less, or other way that the prediction will be better and the predicted sample will be very much close to the actual sample, and with that you can able to by look at the error will be less in case of voiced speech, right. Whereas in case of unvoiced speech, if you see that the error is reducing, but if you look at for a different for the same prediction order, the error that observed for a voiced speech segment and the error that was observed for unvoiced speech segment, there is a lot of difference. So, this is because the reason is that in case of unvoiced speech segment, as the samples are not correlated, or the speech signal itself is observed to be noisy, and in case of noisy, you can able to see the samples have the random amplitudes, and from the random samples, the predicting the signal or the sample will be leads to the erroneous result and all. So, the next thing that here we are going to discuss over here is that And so far actually we have done the LP analysis for in view of synthesizing the speech. It is nothing but generation of a speech, and we also carried out the analysis for in view of error, that means for computing the prediction coefficients. We have carried out the analysis phase, carry out the LP analysis for vowel segments. So, you know that the vowel segments are nothing but the voiced speech segments, right. All vowels are produced due to the vocal folds excitation, correct. So, therefore, for all the vowel segments are nothing but the voiced speech segment, and in case of voiced speech segment, and here we consider the example for a vowel will be the E. It is a front vowel. You can see E is a front vowel because the tongue hump will be at the frontal portion of the oral cavity, and here you can see we just considered the like around 25 milliseconds of the speech segment. It's a part of a vowel, and you can see this is the around 20 or 25 milliseconds of a speech signal for the from the portion of the vowel E. And here if you apply apply the LP analysis, or if you model the LP model for this particular speech segment, and if you compute the linear prediction coefficients corresponds to this particular frame, and then if you analyze the error that will be associated for this particular speech segment, right, you can able to observe here the second plot is nothing but the error plot. The first one is the signal, the speech signal, and here this speech signal is part of a vowel segment. The vowel is E. So, this is the voiced speech, right, and here for this voiced speech, using the analysis model, right, you can able to first compute the LPCs, linear prediction coefficients, because how do you compute? We will compute the linear prediction coefficient by minimizing the error that we have seen. We will get a set of normal equations, and by solving that normal equations we will get the optimal set of coefficients are known to be scale factors. So, those are the LPCs corresponds to this particular frame, and then by knowing this for this in estimating those LP coefficients, you can able to observe that like in analysis model the outcome is the error signal. So, if you look at the error signal, or if you plot the error signal corresponds to this particular speech segment, you can able to see that the error is observed to be like this. And here you see that at the beginning you can able to see the error will be, and here one more thing you can able to observe here that the signal is varying from like the amplitude, if you look at here, almost like close to minus 5000 to plus 5000. The signal variation is minus 5000 to plus 5000, whereas if you look at the error magnitude will be, you can able to see it is about minus plus 1000 to it is varying from around minus 1300. So, the error magnitudes are less, and then on top of that if you look at here, you can able to observe the error at the beginning, because here this is the signal starting point, and prior to that we have no knowledge about the signal at all. We have no knowledge about the signal. So, therefore, at the beginning of a signal, when you try to predict the signal component at the beginning, so where you can able to encounter the more error and all, because it is obvious, because when you try to predict the very first sample, for that there is no history at all, because we do not know, because we are just beginning, our prediction starts at this point. So, we do not have any previous sample. So, therefore, we can able to, here we have to guess the sample amplitude randomly. So, therefore, that leads to error. And then when you come to the first sample, you have the 0th sample is available, because just now it is observed. So, that becomes your history, and with that knowledge you have to predict the first sample. So, that way the initial samples, since we require here this LP analysis is carried out with the P samples, right, the P may be around 15 or whatever, but here since at the beginning, since we do not have the P samples, so therefore, you can able to observe the higher error at the beginning of the prediction, at the beginning and after that, since we know the actual samples. So, with that actual samples we will try to predict, and you can able to see here there is a minimum error, there is the error is very less, the error is very less, and after that here you can able to see there is a sudden increase in the error. There is a sudden increase in the error. So, here this sudden increase in the error is because of the impulse or the excitation, because you can see that till this point there is no speech at all, right, and here at this point we just started to produce the speech, and here we know that this is the vowel region. So, the vowels are produced by like the sequence of the periodic excitation. So, the periodic excitation here is offered by the vocal folds. So, the vocal folds will be opens and closes, vibrate, and because of the vibration of vocal folds, you can see that the sequence of pulses or sequence of impulses will be generated. That acts as an excitation and all. And since here the impulse, that means here the vocal folds will be suddenly closes. So, with that the impulse will be generated, or a pulse has been generated, narrow pulse, and that is not known. That is because this is an impulse. You know that the nature of impulse will be in a short span. You can able to see that the signal will be fluctuated a lot. In a short span, the signal amplitude changes a lot suddenly. So, this is not aware. That means by looking at the previous samples, you cannot predict this sudden change. So, that is the reason that you can able to observe the error at the at this portion. This is nothing but glottal closure at the instant of glottal closure, because at the instant of glottal closure the vocal fold suddenly closes. Because of that the impulse will be generated, and that will be propagated through the oral cavity, and then you can see that the resonances of the vocal tract will be superimposed on it. So, here you can see this maximum error, or you can say the high error is observed because of that vocal folds closing and the closure of vocal folds. Because of that a narrow pulse will be generated, and because of by looking at the preceding samples, you cannot predict that the sudden change in the excitation, and that leads to error, and that you can able to observe as an error and all. And once after that you can see that the signal fluctuates over here, and then again you can able to see after some point again you can see there is a higher the maximum error, or a very high error signal is observed, signal amplitude is observed. Here also again, here at this point again there is a glottal closure, because here you can see the vocal folds will be opens and closes. At the time of closing, vocal folds will be suddenly closes. So, with that the narrow pulse will be generated, right, and the narrow pulse like observed to be like an impulse, and since the impulse means still that the signal nature or the signal variation will be of have certain like correlations, and suddenly now because of the vocal folds closure, glottal closure, the sudden impulse will be generated, and that is not predictable. So, because of that you can able to see the error here, you can able to see the higher error both at the negative and positive side and all. Here also you can see, here you can able to see the error in the negative and positive side, and here also you can able to observe the highest error, or you can say the maximum error over here and all. And here this is because of the vocal folds closure, or the generation of impulse due to the vocal folds closure, and since the impulse characteristics are very different from the previous samples, so therefore the prediction will be very poor, and that leads to the maximum error and all. So, therefore, in case of voice segment you can able to observe that the errors you can able to observe at the places of glottal closure, because whenever the narrow pulse will be generated, and that is not predictable. So, because of that you can able to observe the error signal in the LP analysis and all. You can see here this is the maximum error, this is the maximum error and all. So, that way if you analyze the voice segments, you can able to see the error will be like, you can able to see in the error you can see that the maximum error is observed periodically at the glottal closure instants and all. The maximum error is observed periodically at the glottal closure instance. So, here you can see the very high error here around this region, and again here also you can able to observe very high error, and likewise here, since it is in this frame we have two glottal closure instants at this point and here at this point. So, correspondingly here you can able to observe the maximum error over here, and here also maximum error over here, and here during these portions you can see that the error is fluctuating between positive, negative and all with reasonable amplitude. So, it means that here you can see the signal fluctuations over here, and since even the sample correlations are less, or signal fluctuations are more, so therefore in the prediction process that leads to some error. So therefore that error will be observed as the fluctuations over here and all. And but here you can see a sudden error, peak in the error, and here also you can able to see the peak in both positive and negative side is observed. This is because of at the locations of glottal closure, as I mentioned in the voicer speech, the vocal folds vibrate. At the time of glottal closure, a sudden impulse will be generated, and that cannot be captured, because at the sudden impulse when it is propagated through oral cavity, and because of the vocal tract response, or these resonances will be superimposed on that. So therefore you can able to see the maximum signal at the glottal closure regions and all. And so that sudden change in the signal amplitude at a glottal closure regions, they cannot be predicted from the previous samples, and hence you can able to observe the maximum error at the periodic locations, or at the locations of glottal closure in the voicer segment. So this is an important observation, and these also match to our intuition, because in the signal analysis you can able to observe, because by knowing a speech signal you can if you analyze the LP analysis, with that you can get a set of LP coefficients, and in the analysis you can able to see that the output will be error signal. If you analyze error signal, you can see that the error will be maximum error will be observed at the glottal closure instances, or the glottal closure locations. You can see here and here and all, and anyway here is the beginning, at the beginning anyway, since due to lack of the previous samples, you can bound to get error, the higher error over here and all, right. So this is the error signal for a given voicer segment. And then and here if you look at here the third plot over here, you can see in the third plot there are two waveforms, or the two plots over there, and one plot will be there is a smoothed overlap, the smoothed envelope there, and another one is that you can have the ripples, the waveform which contains the ripples, continuous ripples throughout, right. And here the waveform whichever having the continuous ripples throughout, so that waveform or that particular plot is nothing but like the log magnitude plot of the signal. Suppose this is a voice segment, if you compute an FFT, that means if you compute a Fourier transform like a DFT, discrete Fourier transform, and then if you plot that discrete Fourier transform output, that means if you take a magnitude of that, log magnitude of that, and if you plot that, you can able to see that this the rippled waveform whatever is there, it is nothing but this particular signals spectrum, that particular signals spectrum, nothing but the frequency domain representation of this particular signal, or the magnitude spectrum of this particular voicer segment. How do you get that one? If you apply a Fourier transform and then take the absolute of the signal, that gives you the like magnitude, and then take a log of that, then you can able to observe this particular signal, the rippled waveform and all, right. And this rippled waveform, if you look at a very gross level, the rippled waveform has the higher energy or the very high value over here, and afterwards it has a peak over here slightly, and again here you can able to see another peak over here and here and so on, right. And this is the normal spectrum that is computed by using the FFT analysis and all. And now in the LP analysis, right, you can see that by in the analysis phase, in the analysis phase you have the coefficients, you have the LP coefficients are captured over here. Then after that, this vocal tract system is represented by all pole filter. The vocal tract system is represented by all pole filter. So we know the LP coefficients, and then in the all pole filter model, 1 over A of Z, 1 by A of Z is nothing but the filter transfer function, the vocal tract filter transfer function. So for that 1 over A of Z, if you compute the Fourier transform of that 1 over A of Z, and then if you plot that the frequency response of 1 over A of Z, you can able to observe that the 1 over A of Z, the spectrum of that, or the frequency domain information of that will be like the smooth spectra, or you can say that this plot the smooth plot which superimposed, which is just imposed on this rippled waveform. The rippled waveform is the actual spectrum offered by the FFT on the signal, and the smooth just superimposed on that is nothing but this is the LP spectrum. LP spectrum means we got the LP coefficients in the analysis, and then this LP analysis gives you the AK set of AKs, and then the vocal tract filter is nothing but it's a inverse, it's a all pole filter 1 by A of Z, and where A of Z is nothing but consisting of the coefficients of the prediction coefficients, and by estimating the prediction coefficients, if you plug in these AKs in 1 by A of Z, and then if you compute the spectrum for 1 by A of Z, right, you can able to observe that the spectrum is something like this. So, from this it is very clear that the LP spectrum is smoother one, because the LP spectrum is nothing but it captures the characteristics of the vocal tract system. It captures the characteristics of the vocal tract system, right. So, and whereas this one, the rippled waveform or the rippled signal or the rippled plot, it is nothing but it is a spectrum of the entire speech signal, the spectrum of this particular speech segment, and here this is the speech segment where it is it contains the properties of both the vocal tract system as well as the excitation signal also, because the speech signal is nothing but a convolution of the vocal tract response with the excitation signal. So, therefore, this rippled waveform or the rippled signal is nothing but the spectrum of the speech signal or the voice speech segment, whereas this LP spectrum is can be contributed to more towards the spectrum of the vocal tract component of a speech signal. So, that is the reason that if you look at the spectrum offered by the LP analysis or the LP filter or this linear prediction filter corresponds to the vocal tract, where the spectral envelope almost follows the original signal, and here these ripples are basically due to the excitation, because as you seen the excitation is for generating this particular speech segment, it is nothing but a periodic train of impulses, right, a periodic pulses or periodic impulses. So, these periodic impulses, that periodicity whatever offered by the periodic impulses, so that acts like a ripple, and since the speech signal is a combination of both the properties of the excitation as well as the vocal tract system, that is the reason that you can able to see the speech spectrum will be the rippled one, and here the gross trend of the rippled waveform is nothing but the vocal tract response, where the rippled version, the rippled signal is nothing but it is due to the spectrum of the excitation signal, because the excitation signal is a periodic trend. So, for a periodic trend, again in that the fundamental frequency or the periodicity of the signal is the more dominant frequency that is offered by that. So, that you can able to say ripple throughout the spectrum and all, ripple and its harmonics, right. Whereas here you can, if you look at the bottom, the fourth plot, this is nothing but the spectrum of the error signal, So, this is your error signal, right, this is your error signal, and if you look at here, this is the spectrum of the error signal, right, error signal. And here what is error signal here? In case of voice speech, right, the error signal will be periodic signal, like the periodic pulses. You can see here this is a pulse here, the impulse, sudden impulse over here, and afterwards here there is a impulse over here. So, likewise this is a periodic pulses, a sequence of pulses or a periodic pulses. So, since it is a periodic pulses, so if you look at the spectrum of this particular signal, you can see all frequencies are present, or it is nothing but here, since it is a periodic pulses, right, and so the dominant frequency component is nothing but associated to the period of the signal, right. So, whatever the period of the signal, you can see from the ripple, you can able to see that the ripple frequency is nothing but the period of this particular signal and all. And since it is a periodic signal, you can see the error signal will be, and we know that this error signal will be fluctuating and kind of a random noise and all. So, all the frequencies are present, but at the same time the periodic component is dominant one. So, that is the reason that you can see all the frequencies are present, and the ripple is mainly due to the periodicity that is offered by this voiced segment, So, that is the reason that if you analyze the error, the spectrum of the error signal, right. So, since it is it is a noise, it is a like noise. So, therefore, the spectrum is flat, like all frequencies are present, right, and this is a periodic one. So, that is the reason that you can able to find the harmonics of the periodicity can be observed over here and all. So, therefore, here if you look at here, the error signal spectrum will be this one, right, and so in this LP analysis we can able to see the kind of separation of the vocal tract and the excitation, right, vocal tract and excitation. We see in the analysis phase, this is a particular speech segment to be analyzed, and then from this speech signal in analysis phase we will get set of LP coefficients, and then the outcome will be error signal, right. And now for this, if you plot the if you compute the spectrum of the vocal tract, is nothing but 1 by A of Z. If you compute the spectrum for 1 by A of Z, you can able to see that there is a smooth spectrum, like you can see that the line, this plot, that is superimposed on the true spectrum. The true spectrum is nothing but the spectrum of the speech signal, and the speech is nothing but it is a combination of the vocal tract response and the excitation signal, right. And here what we can able to attribute here is that the smoother spectrum that is observed to be like a superimposed on the envelope of the speech spectrum. So, this is mainly contributed by the vocal tract system, right. And here then this is the error signal, and for this error signal if you try to compute the spectrum, is nothing but just apply a Fourier transform on for this particular error signal, you can able to see the spectrum is like this, the spectrum of error signal is like this, right, and now you can see in this the spectrum of error signal, where if you look at that the spectrum is almost like flat. That means that for all the frequencies you can see the amplitude is more or less similar. The amplitude will be like it is about 75 dB or 76 dB, like at low frequencies have 76 dB, and the mid frequencies also 76 dB, and if you look at the end, the high frequencies also offering the same gain, same energy of about 75 dB, 76 dB and all. It means that it is almost like a flat spectrum, right. And another thing to be noted here is that the spectrum observes to be like, you can see there are ripples. So, the ripples are nothing but harmonics that are harmonics corresponds to the periodicity here, So, therefore, this is your error spectrum, right, and this is your vocal tract spectrum, like the smoothed one is a vocal tract spectrum. And now, if you look at here, the speech signal is nothing but the convolution of the vocal tract response with the error signal, right, or the excitation signal. Here the error signal is nothing but your excitation signal, because here if you look at here in the speech synthesis phase, like your input is the excitation, and then you have LP filter, like is nothing but vocal tract filter. The output is the speech signal, and that we can call it as a generating filter. Whereas in the analysis phase, we perform the reverse analysis. That means we have a speech signal is available for us, and from that we have estimated the LP coefficients. We have tried to estimate the LP coefficients, and then after estimation you can able to see there is some error in the prediction. Right. So, therefore, we can see the generative filter and the inverse filter, or you can say that the analysis filter, they are exactly reciprocal to each other. So, therefore, whatever the output of the analysis filter is nothing but the input of the generating filter. So, therefore, output of the analysis filter is nothing but the error signal, right. So, it is nothing but the input of synthesis filter is nothing but the excitation signal. So, therefore, here whatever the error signal we are saying, this is nothing but the excitation corresponds to this particular speech signal. The excitation, that is this excitation corresponds to this particular speech signal, right. And here this excitation, this is known to be excitation signal, and this is also known to be residual signal or linear prediction residual signal, because in the linear prediction analysis, using the linear prediction coefficients, we try to predict the speech signal as as far as possible. But still there are certain locations where you cannot or you are unable to predict the speech signal properly. So, that leads to the maximum error and all. So, therefore, you can see this error signal can be viewed as the residual signal. It means that in the linear prediction analysis, we will try to predict or we will try to predict the speech signal as far as possible using the linear prediction coefficients, but at and this signal is nothing but it is a prediction error. That means, here in the prediction process, this is the error that was observed and all. It means that in the linear prediction analysis, you will get this at these places whatever the amplitudes are there, this is the corresponding error and all. So, therefore, we can view this as a residual signal. It means that in the process of prediction, so the signal or the prediction process or the LP analysis is not able to capture or not able to properly predict the signal. So, therefore, you can say that this is going to be linear prediction residual signal. Residual means which is the remaining, that means whichever is not captured, whichever is not predicted, right, the remaining part of the speech signal which is not at all predicted, it is going to be the linear prediction residual and all. So, that is the reason that in the process of when you are designing the generative filter, the signal whichever is not predicted, whichever is remaining is remained from the prediction, this is used as the input to the generative filter and all, input to the generative filter, so that you can get a proper speech outcome and all. And now here what I am conveying here is that, as we know that the speech signal is in the framework of linear system analysis, speech signal is a convolution of the excitation signal with the vocal tract response, right, in the time domain. In the time domain, the speech signal or acoustic speech signal can be viewed as a convolution of vocal tract filter with vocal tract filter response with the excitation signal, right. So, in a spectral domain, it is equivalent to the product of the corresponding spectra, because the speech signal is a convolution of the excitation signal with the vocal tract response or the vocal tract filter response, right, in the time domain. So, whereas its equivalent in the frequency domain is nothing but the multiplication of their corresponding spectra. So, that you can able to observe over here, because you can see here this is a flat spectrum, right. Here the error signal is a flat spectrum with the ripples, simple ripples, right, whereas your vocal tract filter response is, you can see, very smoothed one, very smoothed one. So, if you want to generate the speech spectrum, it is nothing but if you multiply the LP spectrum with this flat spectrum or with this error signal spectrum, you can able to see the corresponding speech spectrum and all, right. This is very evident, this is very clear, right, because you can see the rippled plot in plot 3 is nothing but the spectrum of the speech segment, spectrum of the the vowel segment and all. And now we separated that, right, when the analysis phase we got error signal. So, for that, if you compute the error spectrum, you can able to see this is the spectrum, right, and whereas if you compute in the LP analysis, we got the linear prediction coefficients. So, with that, if you see the synthesis filter and then if you plot the spectrum of the synthesis filter, nothing but all pole filter, you can able to see this smooth spectrum, smooth spectral envelope, right. And then if you want to get the acoustic signal spectrum, it is nothing but the multiplication of the excitation signal spectrum with the vocal tract filter spectrum. The vocal tract filter spectrum is this smoothed one, and the excitation signal spectrum is the rippled one. If you multiply that, you can able to see that, the signal spectrum, right. So, this way also we can able to carry out the analysis where the speech signal whatever we formalized in the digital model as the acoustic signal is a convolution of the excitation signal with the vocal tract response, time varying vocal tract response. The same thing you can able to observe over here and all. So, this is the analysis of the voiced segments using the linear prediction model, right. And here I am just introduced a new term like LP residual, linear prediction residual. It is nothing but the error signal, it is nothing but the error signal that is generated in the process of analysis, LP linear prediction analysis, right. In the linear prediction analysis, the input will be a speech signal, right, and for this speech signal while trying to minimize the error, we will compute the set of coefficients, right, and then whatever the minimum error that is observed for the given set of coefficients. So, this is known to be error signal, right, and this is also known to be excitation, right, and this is also known to be linear prediction residual. So, all the terms means the same. Now, you can see here, this is the plot again the linear prediction analysis for another vowel A. Earlier one is the linear prediction analysis for the front vowel E, whereas here it is a linear prediction analysis for the vowel A, like it is a kind of like a slightly back vowel or a mid vowel, you can say that, because the tongue hump will be in the middle or like towards the back, right, and this is the speech signal corresponds to that vowel A, right, and here if you perform the linear prediction analysis, right, by computing linear prediction coefficients, and afterwards if you try to analyze the error, you can see the error will be here, right, more here, right, here you can see the error here, and here also you can see a bit of error, and basically you can see that here these are the portions corresponds to the glottal closure region. This is the glottal closure region, and here also glottal closure region, and correspondingly you can able to see the more error will be there. You can see the higher error, right, and here also you can have higher error, and there are other places from here also again you can see here again you can see the error over here, and you can also see the error over here also, right, you can see some error over here, right. So, because here the error, anyway this is at the beginning, so therefore you have error over here, and here these are the regions, because here you can see the glottal closure may be around here and all, and here yeah, maybe due to some discontinuity or here you can able to observe here reasonably the higher error, right, and here also here anyway this is a glottal closure region, you can have the higher error over here, and here also you can able to see somewhat a reasonable amount of the error is observed over here and all. Yeah. So, basically here you can see this is the way the error signal used to be, and you can see notice here that at a glottal closure regions you can observe the maximum error and all, and here the same thing whatever we discussed in the previous with respect to the previous plot, the same analysis can be done here for this particular error signal. If you plot the spectrum, you can see the spectrum is almost like a flat. You can see flat means I am saying that the overall the envelope seems to be like a flat, right, but here the ripples are basically due to the periodicity that is offered by the error signal, because here you can see this is the voiced segment. So, therefore, it is obtained by the periodic excitation. So, this periodic excitation will be reflected as the ripples, because the periodicity you can able to see the can be reflected as harmonics in the spectrum. So, therefore, you can see these ripples are mainly due to the periodicity offered by the vocal folds vibration and all. And since it is an error signal and the nature of the signal will be noisy, so therefore, for all the frequencies are present with a uniform or with a almost like more or less the similar strength, similar energy. And here again you can see here in the LP analysis, so whatever the LP coefficients you get in the minimization of error, and if you plug in those LP coefficients in the all pole filter, and if you plot the spectrum of this all pole filter, you can able to observe the smooth spectral envelope, right. So, you can see the smooth spectral envelope almost like it covers the signal spectrum, but the only difference is that the signal spectrum contains the overall shape or the envelope is almost like matches with the LP filter or this the spectrum, the LP spectrum, right, and the only difference is that the ripples are overimposed on the superimposed on it, because these ripples are basically due to the characteristic of excitation, right. So, that you can able to observe here, like you can have the spectral envelope is almost following the LP spectrum, because the LP spectrum we viewed as this is the characteristic corresponds to the vocal tract filter. So, as a response of vocal tract filter alone, you can see a smooth spectral envelope, and then whereas if you look at the signal spectrum, you can see the characteristic almost follows the same trend as the LP spectrum, but it contains the ripples. So, these ripples are basically due to the excitation, because the excitation contains the periodic pulses, and there is a noise. So, therefore, the noise is nothing but it will be reflected as the contribution by all frequencies, and the ripples are because of the periodicity. So, the same thing you can able to observe the way what we have observed in the earlier. You can see here, maybe here we have a formant over here, the formant frequency here, and another formant over here, and another formant will be here. So, that way the depending upon LP order you can able to see the LP spectrum, and from the LP spectrum you can able to find out the appropriate formats that are present in the offered by the signal spectrum and all. So, now in the next class we will look at the the excitation signals for different types of vowels, different other vowels, right, and as well we also see that how this spectrum varies with respect to the prediction order and all. Suppose as the prediction order varies, how the LP spectrum changes. So, what will be the best prediction order for the given for a speech signal and all. So, those details we will discuss in the next class, and now we can stop here. Thank you.